We have looked at a bunch of principles and rules that aim to ensure good design, and we've shown how failure to follow these principles can lead to flaws. Recently, a group of security professionals in industry, research, and the government got together and formed the IEEE Center for Secure Design. Their goal was to focus more attention on secure design, to reduce the prevalence of security flaws. One of the first activities of the center has been to dig deep into the collective experience of its members and identify and categorize common and dangerous design flaws. And here is their top 10 list. Assume trust rather than explicitly give it or award it. Use an authentication mechanism that can be bypassed or tampered with. Authorize without considering sufficient context. Confuse data and control instructions and process control instructions from untrusted sources. Fail to validate data explicitly and comprehensively. Fail to use cryptography correctly. Fail to identify sensitive data and how to handle it. Ignore the users. Integrate external components without considering their attack surface. Rigidly constrain future changes to objects and actors. We have considered flaws already in many of these various categories. So now we'll spend a little time considering a few more.
The first design failure we'll consider results in authentication bypass. As one example of this, consider clients that are coerced to accept invalid SSL certificates. What's going to happen here is that the client is failing to properly authenticate the server because of the poor certificate. Keep in mind that SSL encrypts a connection to prevent eavesdroppers from seeing the communication between a client and a server, but SSL also, by using certificates, ensures that a client is talking to the server it thinks it's talking to. In other words, am I really talking to my bank or a site pretending to be my bank? The certificate tells you that it's the former and not the latter. Now, if an invalid certificate is presented to a client, a web browser should present a warning. Now, we might wonder how many users will click through this warning, and that's a completely separate question of usability. However, we can also consider the case when the warning is not even shown, and this happens oftentimes with mobile applications that use SSL behind the scenes. That is, they get an invalid certificate and now need to take action. Well, the action they should take is to give the user the opportunity to accept the connection or not, or to take some remedial action. Unfortunately, it turns out, according to research by Fall et al., that many mobile applications fail to take any action and simply drop invalid certificates. This is because during development, those developers often turn off SSL certificate validation just to make it easier to test their applications. There's an important lesson here. Security is not a feature. We have to test not only what should happen, that you can connect to the correct bank, but we need to test what should not happen. That is, if a bank provides an invalid certificate, we should not connect to it. Now, as another example of a failure due to authentication bypass, consider authentication tokens with long timeouts. These motivate brute force attempts to steal session cookies. Recall the Twitter auth token failure that we discussed in the web security unit. On the other hand, making a timeout too short while improving security will irritate users, so we have to find a balance. In general, a way to avoid authentication bypass is to develop good abuse cases. Consider what happens if we violate the assumption of unique knowledge, like of a password, or unique possession, for example, of a key fob. How might an adversary learn a password, or spoof a biometric, or steal a session ID? Understanding these things help us build better defenses. The next design failure we'll consider is bad or wrong use of crypto. I'll repeat what I said earlier. Don't roll your own crypto, whether algorithms or implementations. Instead, use community resources, both on the design and implementation side, to get it right. Another failure is to assume that a crypto algorithm that you do use gives you something that it doesn't. Encryption may protect confidentiality, but it does not always protect integrity. For example, if you encrypt something, someone may be able to tamper with it and fool the party who decrypts it that you've said something that you didn't. Hashing, on the flip side, protects integrity, but not confidentiality. So you can be sure no one tampered with your data, but you can't be sure that they haven't seen what it contains. You also need to make sure that you use crypto properly. I've already mentioned once before generating keys with insufficient randomness. You might also fail to generate keys of sufficient size, making your algorithm, your ciphertext, subject to brute force attacks. You need to also make sure you protect the keys from compromise. For example, don't hard code them in binaries that your clients have access to. There's a lot to learn about cryptography, and we won't say much more about it in this course. But if you're interested, I recommend you check out Jonathan Katz's course on cryptography that's also part of the Coursera cybersecurity specialization being offered by the University of Maryland's Maryland Cybersecurity Center. The next design failure we'll consider is ignoring which data in your application is sensitive. Now, it should go without saying that you need to think carefully about the sources of data that you're manipulating in your application. Which of these require protection? Obviously, things like personally identifiable information or geolocation data due to sensor readings or cryptographic keys require protection. The problem is when you fail to identify data that requires protection and then expose it to general access. One example of this was the failure of the iOS designers in an earlier version of the iPhone back in 2011 to appreciate that geolocation data was being collected in a file called consolidated.db. This file ended up containing all of the locations that the phone went. Now, this was not due to some big brother goal that Apple had. Instead, it was just an oversight to remove the file or prevent it being captured on the phone. When considering the data sources that you may need to protect, you want to ask yourself, how are these data sources exposed? Are they exposed when the data is at rest or when in transmission? And what's the threat model? So if they're exposed at rest, you might want to encrypt them. If they're exposed in transmission, you might want to use an encrypted connection technology like SSL. One possible failure for authentication is to embed an authentication token in an exposed URL. This fails to appreciate that an adversary could watch network traffic and see that exposed URL travel across the network and thereby steal the session ID. Finally, we want to consider how data and its exposure changes over time. We can't just look at the application when we deploy, we have to look at each updated version of it to make sure that we continuously keep it secure. The last design failure we'll consider is ignoring the attack surface of external components. The attack surface are the elements of a system that an adversary can attack or use in an attack. And the question is, when you build a system that involves third-party components, how do these components contribute to my overall attack surface? Do they only do what I want and nothing else? Consider the recent shell shock bug, which is a bug in the bash shell. Bash is often thought of as just a local shell that receives and processes commands. But it turns out to also be a third-party component in other servers like the Apache web server, which it uses to run CGI applications to generate dynamic content. It's also used by OpenSSH and DHCP servers. The failure here is that the bash shell, which is used by these sites, is far more powerful than necessary for these particular tasks. It really shouldn't have been used in the first place. As a result, a failure in bash now leads to a serious vulnerability in many network-facing servers.